thing that you're not understanding, so please, after the presentation, you can definitely contact me. Okay. So I'll make it short and I'll make it as simple as possible. So the topic is going to be on the hydromechanical behavior of expansive soils under varying saturation levels, or let us say under varying water content levels. So in this process, we are going to cover the basic topics of what expansive soils generally are, okay, and then the thing called landfills, okay, what is it, what are its components, and how to design them, and then a particular case study that how this study on expansive soils is going to help design parts of landfills. Okay, so that is what is the hydraulic performance and mechanical behavior of bentonite sand mixers about. We will deal more about that when about this bentonite sand mixers when we discuss about the specific part. Okay. So first, let me tell that what an expansive soil generally is. Okay, so generally, soils have a tendency to change in volume when water is added to that. So some soils may undergo a huge amount of volume change. Some soils may undergo a very less amount of volume change. So soils that undergo a huge amount of volume change, or let us say significant volume change, are generally termed as expansive soils, and they are characterized by very specific mineralogies, like let us say monomillonaterite. The problem with these soils is that when you use them in typical field conditions or in real life, they have very low permeabilities, okay, and high water. They can absorb a very high amount of water, due to which they have a huge volume change, and they in certain cases they are also characterized by very low strength. Okay, like for example, in this case, this pavement is made of, I mean, its base is subgrade layer is made up of expansive soils. So when what happens is that if you make a subgrade layer made of expansive soils, then under rainy season, or let us say under winter season, okay, or under summer season also, what will happen is that they'll undergo something called changes in volume. Okay, so if it's a summer or winter, since where the temperature is uh, varies from high to low and the humidity is very low, they will undergo evaporation, as a result of which there will be a significant decrease in volume, which we term as desiccation. Okay, on the other hand, in the rainy season, what will happen is that there will be a significant increase in volume, which we term as swelling. This consecutive cycles of swelling and desiccation will cause these cracks. Okay, and you don't want this type of cracks. You may have also observed certain type of cracks in foundation level also. Okay, so these are mostly due to the problematic soils. Okay, this type of soils. So that is one context. Okay, in other contexts they are also very useful. You see, since they are characterized by very low permeability and they have something called very high volume change, they are mostly useful in designing something called cover systems. Okay, like this. Okay, like this yellow part that you are seeing right now. Okay, that is a cover system. Okay, they are useful in this kind of things. So we'll focus. Well, no, we are not. So in our this particular case study, we are going to focus on the beneficial aspect. We are not going to focus on the I mean, we're not going to focus on the detrimental aspect of the expansive soils. Okay. So in order to focus on the beneficial aspect, first we must know that what a landfill is. So often people have seen this kind of like garbage dumps. Okay, and these type of dumps are mostly like termed as, in technical terms, non-engineered waste dumps. Okay, non-engineered waste dumps means you're putting just the garbage, a lot of garbage, in just an unprotected manner. Okay, and in those cases, what happens is that these garbages react with, let us say, different types of environmental systems like rain, sun, soft mass of soil, soft mass of garbage that may actually cause failures. Okay, and when it fails, then what happens is that it may, the percolation, or let us say the water that actually passes through this garbage, that may pass through the soil layer and may contaminate the groundwater, and we generally don't want that. Okay, this specific term for this type of thing that contaminates the groundwater that passes through the garbage is termed as leachate. So you can say that the rainwater interacts with the waste, it forms a leachate, and then it contaminates the groundwater. The other point is that these reactions that happen due to the falling of this rain or under the sunlight, or let us say under climatic changes, leads to decomposition of the waste, and this decomposition leads to formation of gases. These gases are mostly methane in nature, and that may cause fire hazards. Okay, a very good example of this, is a Ghazipur. Okay, Ghazipur has an open dump waste, and almost every year you can see that parts of Ghazipur of this open dump waste are always on fire. This is a example from April 2024. You can see the newspaper. Okay, it happened like this. Okay, and when such a fire happens, it is very difficult to take out the fire. Okay, and it will cause a huge amount of pollution. So the best thing is that to protect all these kind of things, you need something called as a engineered waste landfill. Okay, engineered waste dump. Okay, not a non-engineered waste dump. And an engineered waste dump is what is termed as a landfill. Okay. So typically, it is a way of controlling the method of disposal. So you have, this is a typical structure of a landfill. You have a layer of, I mean, you have a layer of soil. You have a layer of barrier below. You put the all this yellow colored thing is what is the actually the waste dump. You put all these the waste inside it. Okay, and then you protect it with a cover, with something termed as a cover system. Okay, so what happens is that if you put this entire I mean if you put this entire dump within this cover system, what happens is that it prevents, the main objective of this cover system is to prevent the interaction of the waste with the atmosphere. With the atmosphere, if it doesn't interact with the atmosphere, then the process of decomposition will be less. That is the first thing. Even it decomposes, the cover system actually prevents the these gases to come out. So if this prevention happens, then what happens is that the ability, there's foul odor, then then this tendency to catch fire, all these things will be minimized. That is the job of this yellow, of this green colored thing. On the other hand, this gray colored thing that is present at the bottom, this will prevent the leachate. Okay, it will prevent the leachate to come in contact with the groundwater. So in both ways, actually, this cover system is protecting the environment from this waste. Okay, now there are many ways in which basically you can prepare a landfill. Okay, so these are the different types of landfill. We are not going to go into the details of that. Okay, but you should understand this, that preparing an engineered landfill takes a, it takes a lot of things to actually decide. Okay, and we'll see that how the design of this landfill is actually done. So these are the main basic components of the landfill that we'll see one by one. So the first component is the bottom and the sideliner system. So as I've said earlier, that the bottom and the sideliner systems are the part. I mean, this green colored barrier that you are seeing is the bottom and the sidelining system, and this prevents the leachate to come in contact with the groundwater. So it protects the groundwater, and it also protects this. I can also say this. You can also say this. It also protects the nearby soils also. Okay. The top liner system, okay, at the top that is present, it prevents the interaction with the atmosphere. Okay. So let us say if there is a rainfall, okay, the rainfall may not immediately come to the west, because if it immediately come to the west, then what will happen is that immediately reactions will happen, and then the gases may come out. Okay. To prevent that, okay, to prevent this percolation, to prevent this infiltration to happen, the top liner system is there. Okay. You also have something called the leachate collection and removal system. Okay, like if there is excess amount of leachate, okay, then you may also remove the leachate. You also have the gas collection. Okay, when there is an excess amount of gas happens, you can also have this gas collection. And mind you that this gas collection system can also be useful. Okay, it is also useful to, I mean, to prepare biogases. Okay, so the methane that comes out can also be useful. Okay, can also be useful for household purposes. So in certain cases, landfills are engineered in such way so that you have this gas collection system pipes that you can utilize it for other purposes. Then there is a stormwater management system, environmental monitoring system, and obviously there is a leak detection system to check that whether these cover systems are working perfectly or not. Okay, so that is why you have something called this groundwater monitoring system. Okay, the eighth number. Okay. This is because to check that what is the pH level of the groundwater from time to time. That whether there is a, whether due to the landfill or anything. Okay, whether the pH level is increasing or not. Okay. Now, when we talk, we will be talking specifically about the bottom and the side lining system, and we will be talking specifically about the top cover system. So, when we will be talking about the bottom and side lining system, okay, as I've said earlier, the main job of the bottom and the side lining system is to prevent. Okay, the main job is to prevent the leachate to come in contact with the surrounding soil and the groundwater, because if it comes in contact with the groundwater, the first thing that will do is that it will contaminate the groundwater, and that is why the bottom and the side draining system is made up of multiple barriers and multiple drainage layers. Okay, so this is how the bottom and the side lining system looks like. Okay, so uh, you have first a compacted clay liner. Compacted clay liner is a clay soil. Okay, and this soil is generally expensive in nature. Okay, so it may not be highly expensive. It may be moderately expensive. I mean, it may expand to a certain extent. Okay, and there is a reason why it is expensive in nature. Okay, and it is compacted. It is not like in a very loose state. Okay, and then you have a layer of geomembrane, you have a layer of geotextile, and then you have a drainage layer. The main job of the geomembrane is to prevent the drainage particles to come in contact with this compacted clay liners. Okay. In more nowadays, people use a double barrier system. So they have a compacted clay liner, then they will have something called the geosynthetic clay liner. Okay, a geosynthetic clay liner also has a layer of clay that is sandwiched between two layers of geosynthetics. Okay, it is, you can say, as a subsystem extra barrier system. When the compacted clay liner actually, it may not work, or it may become clogged. In those cases, the geosynthetic clay liner system will work. Okay, and the next part is similar in nature. Okay, these are the two other these are the two other types of arrangements. Okay, there may be multiple arrangements. You can have, like, you can have a collection pipe at the top, you can have a drainage layer, an additional drainage layer at the top. So these kind of collection systems are there. Okay, the collection pipe is meant to collect the leachate. Okay, and the additional drainage layer may prevent the first, it may prevent the first percolation of the leachate when it comes to the waste. Now, this is how typically the schematic of a single liner system looks like. Okay, so you have this brown colored thing called the compacted clay liner that generally varies at a, that generally the height of which is from zero point 0.5 to 1 meter. So it's not that thin. It is highly, it's comparatively thick in nature. Okay, and the main job of this is to prevent, as I said earlier, also to prevent the flow of the leachate. Okay, then as I've said, you have a geomembrane followed by a layer of geotextile. Then you have a collection system, leachate collection system, and then you have the drainage layer and the gray colored waste at the top. Okay, now you see, in certain cases, what happens is that the temperature inside the waste, okay, especially when the reaction undergoes, the temperature inside the waste may increase subsequently. And as I have said, that clays, as these expansive clays are subsequently, are very sensitive to temperatures. Okay, so what happens is that when the temperature increases, then the clay continues to dry, and this dry causes the desiccation of the clay layer. Okay, now in order to prevent that, okay, in order to prevent this flow of this, this increase in, the desiccation of the clay layers. Okay, mostly the temperature inside the waste system is somewhat kept as constant. Okay, in order by, keeping the reactions at in hand. Okay, the second way is that you also need to prevent the percolation of the leachate, because that leachate may also come in contact with this clay layer and may also cause the desiccation of this clay layer. Okay, the prevention of this leachate, you know, is, especially the toxic portions of the leachate is prevented through this HDP geomembrane. Okay, the geomembrane is the inert material that prevents, the contact of the leachate with this clay liner. And the geotextile will have two purposes. As I've said previously, that it protects the drainage, it acts as a drainage material. And the second thing, as I've said previously, is that it prevents this, all this drainage material, all this drainage layer is made up mostly of sand or gravels. Okay, so it will prevent this sand or gravel to come in contact with the HDP geomembrane and the compacted clay liner. Because what will happen is that if the sand may or the gravels they come in contact with the HDP geomembrane, they will cause puncture in this geomembrane, and then the purpose of the geomembrane will be lost. Okay, so if the geomembrane gets, if the geomembrane gets perforated, then what will happen is that the leachate will directly flow through this waste and will come in contact with the clay liner, which will cause desiccation. And once it gets desiccated, then what will happen is that cracks will come in the clay liner. And when cracks will come in the clay liner, then what will happen is that the purpose of the clay liner is also lost. So all the leachate will come and flow down to the groundwater. So that is why this double protection system is enabled. First, the HDP geomembrane will prevent the leachate to come in contact with the clay liner. Even if it comes in the contact with clay liner, it won't be that much toxic. So the clay liner will do the remaining job of not or of preventing it to pass it into the groundwater. Okay. The top liner system, on the other hand, acts in a very different way, and it doesn't need so much protection. Okay. So when we talk about the top liner system mostly mostly consists of the same clay layer. Okay, that may be varying from 0.5 to 1 meter, and just a simple layer of drainage, but it doesn't consist, and the geomembrane. It doesn't consist of this extra sand layer, or sometimes the double drainage layer at the top. And in this case, the top liner system is inverted compared to the bottom liner system. It is obvious because the main job of the top liner system is to prevent the rainfall, or let us say, I mean, the atmosphere to interact with the MSW, municipal solid waste. And so what happens is that this 0.5 to 1 meter of this layer of this clay will prevent the infiltration of the rainwater into the MSW. Okay. I mean, if you try to prevent, it's not like that it always prevents in that manner. Okay. But you try to prevent the protection. I mean, it will give a protection to the MSW so that the reaction doesn't become so fast and the temperature inside of the MSW doesn't increase too much. Okay. The second important thing that it does is that, I mean, when the reaction will happen, then what happens is that in such cases, the gases from the MSW that consist of methane, as you have seen, gets exposed to the atmosphere outside. Since these type of materials, I mean, this clays, expansive clays, as I've said, as I've told in the very first slide, that they consist of very low permeability. So they will prevent this gas from coming in contact with the atmosphere. Okay. Even like if the gas exposes out, there is a gas collection system that will, collect the gas. And even if some amount of the gas expressed out, the amount will be very negligible compared to an open dam system. So that is why, that is the main purpose of this protective cover soil. Sometimes you will see that this protective cover soil is actually a layer of the vegetation is provided at the top of this protective cover soil, to give a good look at the top and also to prevent much evaporation of this cover soil. Okay. So this is how typically it looks like. Okay, you have the grass layer at the top, then you have a gas pipe. This is as I've said, the gas collection system pipe. That is basically excess gas is there. That it will collect and remove this excess gas and collect it to be used in household. Okay, as a biogas. And in between you have this erosion layer, or what is a compacted clay layer, that is almost like, zero point 0.5 varies from 0.5 to 1 meter. Then it has this flexible membrane and the geosynthetic clay liner. And these two are just the protective layers that prevents the waste to come in contact with this erosion layer, or let us say the compacted clay layer. Now, you see, we have to design, the main job of us is to design these compacted clay layers. Okay. And mostly if you see, things like, I mean, when people talk about expensive soils, then people mostly talk about black cotton soils. Okay. But you see, black cotton soils are not very effective in designing this type of clay layers. Okay. You see, mostly because there are many reasons that how it has to be designed. Okay. The most common design, or the most common process of designing the uh, this type of clay layers is by considering bentonite. Okay. Now bentonite is commercially available. Okay. So this type, when I'm talking about bentonite, it's a highly expensive clay that is commercially available. Okay. And it may be in powdered form or maybe in granular form. Okay. But this bentonite itself, has is highly expensive in nature. So when a material is highly expensive in nature, then what happens is that if it's like under this, I mean, when a soil is highly expensive in nature, if it's under climatic condition, it will undergo huge desiccation, or it will undergo huge shrink. I mean, huge settle. I mean, huge volume change. Okay. So to prevent that, we had an inert material termed as, I mean, sand. Okay, to reduce its volume change. Okay, but how much amount you have to add, that is a big question. And these mixtures are effective clay barriers because of typical reasons. First of all, they have a very low permeability and of the order of 1 e to the power 9 meter per second. Okay, they have something, like called, termed as self-filling. Okay, so self-filling thing is that these type of materials show high desiccation, so I mean, so cracks under high temperature and low humidity, obviously, as I said. But when under the exposure of moisture, they can expand and can seal these cracks. Okay, typically like this. Okay, so this is an example of a desiccated bentonite. You can easily see the cracks. But when under moisture, you see that those cracks have been sealed. You can see the cracks. I mean, you can see that where the cracks have been formed. I mean, those images, I mean, those points are visible, but you see that those cracks have been sealed. So once the sealing is done, which we call the self-filling, then the purpose of the liner system is actually, it's like it's done. Okay. So that is why we generally prefer this type of systems as, in the liner systems, both in the top as well as in the bottom corners. And if you mix it with the right amount of sand, it can prevent this excess amount of desiccation and this excess amount of volume change, as well as it can add a little bit of strength to this expansive clays. Okay. So right now we'll see, we'll take two mixtures of bentonite sand. Okay, one of them will consist of 100 bentonite, that means complete bentonite, and the other of them we will see will consist of 20% of bentonite and 80% of sand. Okay, so these are some of the properties of the bentonite sand mixtures. Okay, so this is the liquid limit, the plastic limit, the plasticity index, the soil type. Okay, so the soil type, in the case of the soil type, you can see that it's a fully bentonite, it's a high plasticity soil. High plasticity soil means that its volume change, its settlement, its, let us say, it's if you talk about its permeability, I mean volume change, settlement, its desiccation will be extremely high. Okay, and its permeability, as you can see, will be extremely low. On the other hand, when we mix a huge amount of sand with it, 80% sand means almost like 80% of its weight is replaced by sand. Okay. Now it's no longer, it's no longer a high plastic clay. Okay, but its permeability is reduced significantly. But you see, it's still in the range of 10 to the power minus 9 meter per second. That means we can use it as a liner system. Okay, and we'll see that how it's effective as a liner system. So these are the grain size distributions, the compaction curves. Okay, and for obviously for the bentonites, I mean obviously for the 100% bentonite, the water content will be very high compared to 20 bentonite design, but the water content will be comparatively low. Now, the first important thing is that we're going to check the strength of these bentonite sand mixtures. Okay, so you see, uh, uh, the first study is on the strain rate of the bentonite sand mixture. Now, when you're conducting an UCS, unconfined compressed stress, which is similar to I can say, uh, which is similar to compressive strain. Okay, just determining the compressive strain. Okay, we see that the strain rate doesn't affect the bentonite sand mixture so much. Okay, irrespective of the irrespective of whether you're using 100% bentonite or a 20% or 20 bentonite 80 sand. Okay, and here the strain rate has been performed at two different strain rates, at 0.04 millimeter per minute and at 0.1 millimeter per minute. And in both the cases, we can see like these solid lines are representing for 100 bentonite, while these dotted lines are representing for 20 bentonite 80 sand. In both these cases, we see that the axial stress, which is similar to the compressive stress, we are getting the same values. On the other hand, if you vary the the water content, we see that the compressive stress is actually significantly changing. Okay, it is more in case of with the decrease in water content, it is the strength increases significantly, and it is more observed in case of 100 bentonite compared to 20 bentonite 87. Okay, so you see, till even I can say this, that till like I mean when the water content is too low, then 100 bentonite shows a very high compressive strength. Okay, like around 1800. So from the strength perspective, we can say that 100 at low water contents. Okay, that the more and more it moves towards the, I mean, when the water content decreases, okay, the sample becomes more and more brittle in nature. And you see the failure pattern is not so prominent, okay, in either cases. Okay. Now, since we are looking for since we are dealing with expansive clays, strength is not the only aspect that we should look for. We also have to look at the volumetric behavior. Okay, so when we are talking about the volumetric behavior, okay, we look at two important aspects we look at two different aspects. One is the shrinkage curve. The shrinkage curve actually says that how the volume change occurs when there's a change in the water content. Okay, so these are the two shrinkage curves of 100 bentonite and 20 bentonite descent. And as you can see easily that with the decrease in water content, okay, with the decrease in water content, even there is no significant volume change, but with the increase, 100 bentonite shows a highly expansive nature. Okay, so when there is a change in water content, we can say that the volume change in case of 100 bentonite is significantly more, okay, compared to 20 bentonite descent. Okay, and this is also observable from the from these samples. Okay, so these were the different sets of the samples that were taken during the shrinkage test, and you can see the amount of cracks is very prominent in case of 100 bentonite. You see, the most important part is that even then, okay, even like when you are talking about 20 bentonite 80 cent, okay, even under case of drying, okay, even when you're drying it significantly, even though bentonite is there, the amount of cracks is much less compared to 100 bentonite. Okay, and this this is very important because, as I've said earlier also, in our cover system we really don't want much cracks. Okay, because even though the self-healing property of bentonite will close those cracks, but if there is a period, okay, like if there is a period like in the summer where you are experiencing a huge crack in the cover system, especially in the top cover, okay, then there is a there's a huge problem because it may affect it may affect the gas outcome rate, or let us say in fact that the infiltration rate also significantly. We don't want that. Okay, The second important of the volumetric behavior we are talking about is the behavior of these samples under different kind of loading conditions. Okay, so you can see that here that we will see that how the bentonite sands will behave under different kind of loads. Okay, we have varied the load. The vertical stress is the load. We have varied the stress from 1 to 400 kPa and have observed that what is the change in the volume. The void ratio will indicate the change in the volume of the sample under different water contents. Now here also an interesting point is that I will see that in 100 bentonite, okay, as we move towards the lower water content, okay, the change in volume is almost similar to that of 20 bentonite 87. This CC is the compression index. Okay, the compression index actually indicates that there is a change in volume. Okay, so you see that the CC of this 0%, 0% means when there is no water content in the sample. Okay, is almost is almost same in both of them. It's 0.04, 0.03. But you see, as you move towards higher water content. Okay, as you move towards higher water content, let us say if you take the highest water content of 28%, we see that the volume change is more significant in of 100 bentonite compared to 20 bentonite 87, which indicates that when there is a high water content, there is also a chance that if the loading is applied, in the cover system under any condition, if the loading is applied, in those cases, what will happen is that the 100 bentonite is supposed to deform more compared to 20 bentonite 87. Now that also is not advisable, because if there is a deformation, if there is if there is no confinement and if there is a high deformation under any stress, okay, then the MSW may settle more, okay, which is also not advisable in certain cases. So in this case also you see that volumetric behavior, it is 20 meter 80 sand that is more more suitable for the cases. Okay, so the last and the final part, that whether to that how to check that that these two systems are working, that whether the cover system is perfect or not, is testing under real life conditions. So we know right now that the strength on the strength aspect 100 bentonite dominates over 20 bentonite 80 sand. On volumetric aspect 20 bentonite 80 sand dominates under 100 bentonite. But you see there is a distinctive difference between their permeability. One of them is at 10 to the power minus 12, while the other of them is at 10 to the power minus 9. Okay, and the most important point is that the cover system should be designed, as I've told earlier also, it should be designed in such a way that the percolation should be minimum and the leachate flow should be also be minimum. So that is what you have to test. So in order to test that, what we have done is that we have done a one-dimensional cover model system. Okay, so you see this is the top cover system. You remember that the top cover system consists of a vegetable cover layer at the top, followed by a layer of compacted clay, and the compacted clay layer varies from 0.5 to 0.1 meter. In our case, we have taken it to be 0.9 meter, followed by the MSW layer. Okay, and this climate, or in the second case, you can see that we have put a climate boundary on the top. Okay, to check that whether the climate how it is performing, and we are going to check the net percolation. Okay, net percolation means how much amount of water or how much amount of leachate is actually this compacted clay layer is actually permitting. Okay, for this, we have taken the hydraulic properties of the, this compacted clay layer. So these are the two hydraulic properties, the 100 bentonite layer and the 20 bentonite sand. And both of these are derived from the grain size distribution and the, and the hydraulic conductivity. Okay. So when we are talking about suction, with an increase in suction, means lower water content. So this is the behavior of the water content that this is the behavior at 10 to the power 6 suction, means it is at more and more towards lower water content. So the permeability actually at lower water content decreases significantly, as we can see. Okay, and these are the two inputs that you are going to put in the compacted clay liners. Okay, and this is the climatic boundary condition that you're going to put. So we have precipitation, we have relative humidity, and we have temperature. Okay, so the precipitation we have taken from January 2023 to December 2023. Okay, and the relative humidity variations and the temperatures. Okay, so when we put all these boundary conditions, then we see that this is what is the net percolation that is happening for both the layers. Okay, so the red one is for 20 bentonite 80 sand, while the blue one, the black one is for the 100 bentonite. It is obvious that 100 bentonite having a lower probability will will have a lower net percolation. But the interesting thing that we can see here is that you see that the difference is significantly small. That means 20 bentonite 80 sand is also similarly effective in preventing the flow compared to 100 bentonite. Okay, It's not about, as I've said earlier also, that it's not about the only about the permeability. Okay, it also depends on the climatic conditions, and it also depends on how your things are varying, like how your how your volume change is varying, how your how your water content is varying. Okay, all those things are important, and you see that at the end of the winter season they are almost showing the same level of percolation. Okay, that there is not, there is a not much difference whether you use 20 mm 80 cent or 100 mm as a whole. Okay, in the percolation. Okay, but you get an extra advantage on using 20 bit 80 cent. You see, 20 bit 80 cent is not very much sensitive. This numerical model, this numerical model doesn't take into incorporation the effect of desiccation. But you already saw from the experiments that 20 bit 80 cent actually has lower desiccation and lower cracks compared to 100 bit. So obviously that means that 20 bit 80 cent is a better barrier compared to 100 bit. Okay, 100 bit is not an effective barrier as such. Okay, because it will induce huge settlements. It will also cause significant cracks. Okay, and it will also prevent the percolation almost similar to the process of close to 20 minute 80 cent. Okay, and since that is our main objective, so that is why even on the strength purposes, it's like 20 bit 80 cent is a little bit, it is a little bit, has a lower strength, as a lower strength compared to 100 bit, but still, based on the hydraulic aspects for the cover system design, this is far better compared to 20 bit. It is far better compared to 100 bit. So, sir, I think I will stop here. Okay. So, if you have any questions, you can please ask.
Sir, thank you for your
Yeah.
presentation, sir. I have a
No.
question. The modeling, uh,
Yes.
there is a phase diagram you have drawn, right?
Yeah. Yeah.
What exactly is the happening there? Or like how the climate parameters are affecting the
Uh,
transport
I
and
think I think this one, right? Yeah. Okay.
that one,
So
yeah, yeah.
yeah. So what happens is that I wanted to
Slide 15,
actually,
I think.
yeah. 15. Yeah. Okay. This one, I think.
Yeah, this one, yeah.
This one, yeah. So actually, I wanted to avoid that actually, but anyways, it's okay. You see, what happens is that whenever there is a, whenever you put this climate boundary, what happens is that the system will calculate the evaporation rate. Okay. So when the evaporation rate is calculated, it uses the Wilson-Penman equation to calculate the evaporation rate. So when the evaporation rate is calculated, then what happens is that the amount of, the amount of water that is present in this clay layer, if you start it at a compacted state, we know the water content. So the evaporation, so the Wilson-Penman equation will next detect that how much water is actually going out. Then it will say that how much water is present in the system. So once how much water is present in the system is known, then based on this, this SWCC and this hydraulic conductivity, you will exactly know that what is the permeability of the material. Okay. So that permeability, when it, once you know the permeability of the material, then what will happen is that the infiltration rate of the water, how much water is going through the layer and all those things will be calculated. So that is how
So
the
my
system.
you, you are saying that if you know the evaporation rate and the amount of water,
Yeah, yeah.
basing on that, you will find the porosity, and then you will get the permeability.
Porosity and all these things are already given, sir. These are already given when you are giving the compacted clay layer. So the porosity, void ratio, specific gravity, all these things. Okay, so I already in this
Mhm,
slide, all these
mhm,
parameters like maximum dye density, octave, these are all already provided. Okay, so you have to input those all these
mhm,
parameters. Okay, so it will calculate it accordingly. Okay, these three-phase systems, whatever is there, it will calculate it. What is the porosity? And in these cases, as I said earlier, it doesn't include the volume change. So the porosity is fixed throughout. Okay, so it doesn't consider
mhm,
any changes in the porosity due to deformation, or let us say when there is an evaporation, there will be a when you're dealing with expansive soils, there will be a shortage in the volume, right? So all those things, these are not
mhm,
calculated here. Okay, all those things are not calculated. The porosity remains constant, and based on this, it's doing everything.
mhm, mhm. Questions from the audience can ask, sir.
Yeah, definitely, sir.
So no questions. So
Sir,
let's thank.
sir, which is the
Yeah,
sir, which is the best
yeah.
that is liner, sir, that BS mixture? Which is the best?
The 20 Venta 80 cent actually. Okay. Because out of these two, 20 Venta 80 cent. Okay. You're asking like
Which
the
is
in
the
the
best
case
for
study that
the liner, landfill liner?
I mean, you are asking in this particular case study, right?
Yeah.
The 2080 sand one. Okay. It's because of the fact that, the percolation rate of both of them is almost similar, close. But you see, as I've said earlier also, the 2080 sand has low shrink, I mean, low cracks and, this low desiccation properties. Okay. So when there is a low desiccation property, you are supposed to go with that one. Okay. Because, you don't want too much cracks in your barrier, because if there will be too much cracks, then the water will come through. Okay. So we don't want that. Okay.
Okay, sir. Thank you.
So, uh,
Sir, one more question I want to ask.
yeah, yeah, yeah.
If your water traveling through the system,
Yes, yes.
then it will interact. Will it create any openings or it will create any cracks? Will
I
it
mean,
uh,
I,
like
I
existing
mean,
cracks? Will it grow during when the water travels through it?
no, no, sir. That is what I have showed actually. You see, when water travels to the system, na, then this is what happens actually. I mean, if it flows, I mean, the cracks because it's an expansive clay. So I mean, there will be a huge volume change, so it will heal. The cracks will heal.
Means water will react chemically with the clay and water
Yeah,
will
I
react
mean,
and
yeah,
then
yeah. I mean,
the
not.
clay
I
will
mean,
expand and fill the cracks.
yeah, yeah, yeah. Exactly, exactly, sir.
Okay, okay.
Exactly. Okay, so that is what is called. That is what we call self healing. Okay.
I think I got a little bit understanding, but not that.
I understood that it's a actually offbeat topic actually. So that is.
I'm trying to relate with concrete. Suppose in concrete,
Yeah, yeah. Concrete also uses the same thing, sir. They also uses bentonite also. Okay. I mean, in certain cases, I have seen that they have used bentonite to self-fill cracks actually.
Okay, okay. Okay, sir. Thank you for your presentation, sir. And
Thank you
all
for
the
inviting me.
participants also found this useful. And
Thank you, sir.
thank you.
Thank you, sir.